Welcome to this explainer. Okay, today we are diving into something absolutely fundamental to flight. We're tackling the core components of Week 3, Module 3, and breaking down exactly what gets a drone off the ground. We are going to completely demystify how propulsion systems work.
Think about it for a second. What actually keeps a 1 kilogram block of heavy metal and plastic perfectly suspended in midair? I mean, it kind of feels like magic, right? But it is pure, synchronized engineering. Without a rock-solid propulsion system, even the most brilliant flight controllers and the smartest sensors are literally useless. Propulsion is the absolute foundation of flight.
So here is our roadmap for today. We're going to look at the heart of drone flight, then dive into the brains, our ESCs, before perfecting propeller design, and finally calculating those crucial power-to-thrust ratios. Let's get right into it.
Starting off with the absolute heart of drone flight.
Motors are basically the muscles of your drone. Their entire job is to take electrical energy from your battery and convert it into mechanical rotation so you can generate lift. But, not all muscles are built the same. On one hand, you've got brushed motors. You'll usually see these on beginner drones. They have actual physical brushes inside that create friction, which really limits their lifespan and efficiency. On the other hand, we have brushless motors, which are the modern standard. They use electronic commutation. That means zero physical contact points inside. By eliminating that friction, brushless motors are vastly more powerful, way more durable, and just incredibly efficient. It's a total game changer.
Moving on to the brains of the operation, ESCs explained.
So you've got these powerful muscles, right? But without a nervous system to tell them what to do, they're useless. Enter the ESC, or Electronic Speed Controller. In a multi-rotor setup, every single motor gets its own dedicated ESC. The flight controller might send out a broad command, but it's the ESC that actually receives it and tells its specific motor exactly how fast to spin at any given millisecond. And because of this, ESCs are way more than just dumb on and off switches. They are actively keeping your rig alive. We're talking overheating protection, crucial telemetry feedback, and buttery smooth throttle response. When your drone gets slammed by a sudden unexpected gust of wind, it is the ESC making those rapid micro adjustments to keep the whole thing from just dropping out of the sky.
Next up, perfecting your propeller design.
Okay, we've got the muscles and the nervous system. Now let's talk about the drone's wings. All that amazing motor power means zilch if you can't actually push air downwards to generate thrust. The very first major design factor here is diameter. Larger diameter propellers move more air, which obviously produces more thrust. Sounds like a win-win, doesn't it? But there's a massive immediate trade-off. Pushing all that extra air requires significantly more power from your battery.
Then there's pitch. This one trips people up sometimes, but just imagine a screw going into a piece of solid wood. Pitch is simply how far a propeller would move forward in one single full rotation if it were moving through a solid object. A high-pitch propeller takes a much bigger bite of air, meaning you get much faster flight. But, crucially, it is way less efficient if your only goal is just hovering in place.
Every single choice here completely changes your drone's DNA. Take two-blade propellers. They are incredibly common because they strike a perfect balance between efficiency and thrust. But jump to a 3- or 4-blade prop, you get awesome stability and thrust, which is amazing for drone racing, but man, it will eat your battery so much faster. And material matters too. Plastic props are flexible, forgiving, and super safe for beginners. But carbon fiber, that stuff is stiff, highly efficient, and absolute go-to material for heavy lifting professionals.
All right, let's bring it all together, calculating power-to-thrust ratios.
This is where we get to use pure math to prove how all these isolated components have to harmonize. If you take absolutely nothing else away from this explainer today, remember this exact ratio. 2-to-1. This is the absolute golden rule of drone flight. Your total propulsion thrust must be at least twice the total weight of your drone.
Let's anchor that 2-to-1 rule with a real concrete example. Say your fully built drone weighs exactly 1 kilogram. The combined thrust of all your motors and propellers working together has to equal at least 2 kilograms. That's 2,000 grams. You desperately need that 100% overhead. Without it, you might kinda barely scrape off the ground, but you definitely won't have the excess power you need to hover cleanly or fight off a stiff breeze.
But hitting that 2-to-1 sweet spot efficiently, that's not just about slapping the biggest motors you can find onto a frame. It's a really delicate balancing act of 4 specific variables. Your battery voltage has to match your ESC quality. Your motor kV rating, which is the RPM it spins per volt of electricity, needs to be perfectly paired with your propeller selection. Professional builders agonize over these variables to get that sufficient lift while totally minimizing power loss.
Let's put this into practice with a quick engineering challenge. Okay, I'm putting you in the driver's seat. Your mission, design a rig to carry a 1.5 kilogram camera payload for 20 continuous minutes. Step 1, the math. You calculate that 2x thrust requirement right out of the gate, factoring in the heavy frame, the massive battery, and the camera itself. Step 2, to lift all that weight efficiently for 20 minutes, you're going to grab low kV motors and pair them with large, stiff carbon fiber propellers. Step 3, you have to make sure your ESCs are rated to handle the massive power load those huge props are going to pull so nothing catches on fire. See how it all connects like a giant puzzle? Well, we've covered the muscles, the nervous system, the wings, and the math. So I'm going to leave you with this final thought. If you were tasked with designing a drone for heavy agricultural mapping tomorrow, carrying massive sensors over huge fields, what exact propulsion system would you build today? Think about the motor types, the prop pitch, what your ESCs need to handle. The sky literally is the limit once you truly understand these fundamentals. Thanks so much for joining me for this explainer. Keep pushing those boundaries, and I'll catch you next time.